Okay, I want to use Laplace transform to solve PDEs. So let's do some review of the Laplace transform, which you learned for ODEs. And the definition of a Laplace transform was, if you have a function of t, you take the function, multiply e to the negative st, and you integrate by t from 0 to infinity. We already tried Laplace transform of sine t, and we got this result. Now if you do Laplace transform of cosine t, it will be basically similar to what you have here. So it will be s over s squared plus 1. But then there's a relationship between these two, which is that if you have Laplace transform of integral of f of t dt, that's same thing as s times capital F of s. And there's such a 1 over s, 1 over s. So that if you wait, something's not right. If you differentiate sine, right. So if you differentiate sine, you get cosine. So integral of cosine is sine, right? So if we had this result, then the Laplace transform of sine would be this divided by s, so that s on top would cancel. So that's why you get that. Okay. So that's one thing.
Can you say why divide by s?
So suppose we know this. Okay. Then let's say we apply this. And Laplace transform of integral of cosine t dt, the left side would be Laplace transform, the integral of cosine would be sine, right? On the other hand, if you take the right side and multiply 1 over s, these two will cancel and you get 1 over s squared plus 1. So you recover this other one. Okay. Now for a moment, I can't remember how this was done, but there's an easier one that I can definitely do, which is Laplace transform of f prime of t is s times f of s minus f of 0. Now, let me try to prove this, because it's the one thing that's used for solving ODEs. Okay? So let's start with the left side, and we'll eventually arrive at the right side. So this one here is equal to integral from 0 to infinity of f prime of t e to the negative st dt. And you just have to use integration by parts, which is you integrate f prime, which gives you, if you integrate f prime, you get f. Okay, and then minus, right? Minus 0 to infinity of the thing that you integrated goes into the integral unchanged. So this just goes in there unchanged. But the one that you didn't do anything to, what do? You differentiate, right? That's integration by parts, right? You differentiate e to the negative st. So what's that? That's negative s e to the negative st dt. Because here, s is a constant, and we're doing all the derivatives and integration by t. Okay. So you get that. And then because s is a constant, you can bring it outside. So negative s is brought outside, and negative is positive. And by the way, if you plug in infinity, well, it's f infinity times e to the negative infinity, but there's something that I forgot to say. That this f of t cannot be increasing faster than an exponential function. So for a sufficient high value of s, this times this should be decreasing to 0. Okay? So that's our assumption. So that when you plug in infinity, this should go to 0. Minus, when you plug in 0, you get f of 0 e to the negative s times 0. Right? But that's the e to the 0 part, which is 1. That we don't need to put. That's just 1. Okay? Then minus minus is plus times s of integral from 0 to infinity of ft e to the negative st dt. What's this? What's this part?
What's there?
Huh?
F of s.
Yeah, capital F of s, which is the Laplace transform of small ft, right? So this will be s capital F of s minus f of 0. Okay, why is Laplace transform so effective in solving differential equations? Well, you had a derivative. Differential equations are equations with derivatives, right? What makes differential equations hard? Derivatives. Yeah, you have derivatives, that's why it's hard, right? So if you can get rid of derivatives, you get an easy equation to solve. Yeah. But that's exactly what Laplace transforms are doing. You see, derivatives were there. Do I see a derivative? No, I don't see any. Just turned into multiplication by s. So Laplace transform changes derivatives as multiplication by s, integrals as division by s. Okay. So you could have also obtained this second result by using the fact that derivative of sine is cosine, right? So you take this and multiply by s minus sine of 0, but sine of 0 is 0, so you cover this one. So that can go from here to there. Okay? All right. Yeah, and then there's some other. Well, let's just do one more. Laplace transform of f double prime of t is s times Laplace transform of f prime of t minus f prime of 0. Oh, I should have. So what we just proved can be written this way, or because this by definition is s times Laplace of f of t. If you take this result and apply it to f double prime of t, then if you replace f prime by f double prime of t, then you lose a derivative. I lost the derivative by having an extra s minus the function evaluated as 0. So that's what you get. Right? But then what is that? This one, I have it here. So it will be s times s fs minus f of 0 minus f prime of 0. And then it's going to be s squared fs minus s f0 minus f prime of 0. Okay? All right. So now let's see Laplace transforms in action. I'll do a really simple one. Okay? So let's say y double prime minus 3y prime plus 2y equals to 0, with y of 0 as 1 and y prime of 0 as negative 2. Let's just say that this is a very simple one. We can solve this without Laplace transforms, but let's say we use Laplace transforms. Now let's take the Laplace transform of this entire thing. I know the formula for this one, right? It's this thing, right? But instead of using letter F, we'll be using letter Y, okay? So So let's see, what does this become? It's s squared. Instead of f, I write capital Y, s, minus s times y of 0 minus y prime of 0. So that much is y over y, right? Then minus 3. Now we have y prime, which we use this one for. Again, instead of letter f, we use letter y. S capital Y s minus y 0. And then plus 2 capital Y s equal to 0. Okay. Where by definition, capital Y of s means it's the Laplace transform of y. Okay, so that's the definition of capital Y. Okay. All right. I have the value for y of 0, which is 1. Y prime of 0 is negative 2. So if you plug in all the values that we know of, we have s squared y of s minus s plus 2 minus 3sys. And it's negative 3 times negative y of 0. Negative 3 times negative 1 is positive 3. 3 times 1 would be plus 3 plus 2y of s. And once again, let me stress the fact. What happened here after doing the Laplace transform? We had a differential equation in the beginning. What happened now?
No more derivatives?
No more derivatives. That's the beauty of this. Okay? No more derivatives. But then we can actually gather all the y-s's together. That's s squared minus 3s plus 2 capital Y of s. And if you move this other one to the other side, you get s minus 5. This can be factored as s minus 2 times s minus 1. So you get y of s equals to s minus 5 over s minus 1, s minus 2. Okay. So beautiful, right? We after Laplace transform, we just have an algebraic equation which you can just solve with just middle school algebra, right? Yeah. But wait, there's no free lunch, right? The thing is, we still haven't managed to find what y of t is. This is y of s, right? You have to figure out what y of t is, so you somehow have to go back. So the immediate question would be, is there an inverse transform? Well, there is. There's a formula for it, but it's impossible to use. Rather, what you do is you really want to say, this is some a over s minus 1 plus b over s minus 2. Okay. And you make it into a single fraction back again as a times s minus 1 plus b times s minus 2. No, this would be minus 2, this would be minus 1, over s minus 1, s minus 2. And then if you simplify this top, that's going to be a plus b times s, negative 2a minus b. And you see that has to equal to this and this, so a plus b better be 5 and negative 2a, no, better be 1 and negative 2a minus b better be negative 5. Simply add them, you get negative a equals to negative 4. So a must be positive 4, and then plug it back in here, you get b as negative 3. So what you get is, although we thought we had the answer, wait, this is not the answer. However, we know that that's same as saying y of s is 4 over s minus 1 plus negative 3 over s minus 2. And I know that Laplace transform of e to the at is 1 over s minus a. You can look at your Laplace table, right? So this is Laplace transform of what? Well, it's 4 times Laplace transform of e to the t. Okay, plus, this will be negative 3 times Laplace transform of what?
Negative 2t.
E to the 2t, right? So that means, what must have been the original function y of t then? 4e to the t minus 3e to the 2t. And that's how you did Laplace transforms. That's the class before this. You learned this in that class. Okay? Some of you still remember, some of you may not, but that's how you do it.